In section 6 we'll talk about model estimation. The context is that we have chosen a parameterized model structure, for instance an ARX model structure, and it might be because we want to do prediction, or we have chosen an output error structure because we're interested in simulation. Well, anyway, we have fixed the model structure. Let us assume that it's an ARX model structure. Well, then we have to fix the number of parameters. Data is going to live in some set RD, and D in this case is NA plus NB, right? So the parameterized model structure with all the possible thetas gives you a model set, right? And then of course you have done experiment design and you have collected data and data points. So this means an input and a corresponding output on your system, right? And then the question is, how can you use the data to select a theta in your model set? Well, such a mapping from data to an estimate is called a parameter estimation method, and in this course we'll focus on prediction error methods, although there are other methods available in the literature, but they cannot be taught in a 15-hour course. Well, parameter estimation methods, this means that we're going to judge the model by its ability to predict the observed data, and predict is very important because we do not say simulate, right? If we had said simulate, we would only be using inputs, but we say predict, so we use past inputs but also past outputs, right? So using a model, a data set, we can compute the prediction errors, right? Sometimes I call them the residuals. And the idea is that, well, you have to select your estimate in such a way that the prediction errors or the residuals become as small as possible. And now, of course, we have to qualify what we mean by as small as possible. The residuals, the prediction error, are living in Rn because we have n data points here. So in order to qualify how large the residuals are, well, you have to use a norm in Rn, right? So here is our setup. In general, we'll work with the filtered residuals, where L is some stable filter. If you don't want to filter the residuals, well, then you simply take LQ is equal to 1, but the idea is that you can orient the fit in certain frequency regions. And what we'll do is use the following norm, right? It's 1 over n, sum over all the data of some positive function of the filtered prediction errors. What we mean by positive is, for instance, that this function is, for instance, if you have x here, that you have x square, or the absolute value of x. And of course we need to generate an estimate. Well, the estimate will be the argument that will minimize this function Vn. Well, it's based on n data. It's based on, well, a parameter vector and this data set. So this is really prediction error identification. So here is our setup in summary. We work with the filtered prediction errors. So here you have a design parameter LQ. You work with the norm, but in practice in this course will work with simply squared, right? So Lx is x squared, and then, as I said, you can obtain a parameter estimate, and this is prediction error identification, right? So there are many variants. As I said, you can play with the filter, you can play with the norm, but in practice you will always take, well, function squared. Of course, here you can play with the different model sets. So for instance, you can choose an ARX, an output error, and then once you have selected the model structure, well, then you can also play with an A and B, right? This will not be explored that much in the course, but also the minimization method is something you can play with. We will see that for ARX models, in our case it will be least squares, and for all the other model structures we'll have the use of iterative methods like the ones that we've considered in the optimization course of last year. So before we talk about the choice of LQ, remember that the one step ahead prediction is h minus 1 q gq u of theta plus 1 minus h minus 1 q y of t. Okay, so epsilon t minus 1, so that's the residual, the prediction error, is y minus the one step ahead predictor. So that will be y minus this one, so minus y here. This will be compensating, and then we'll have minus h minus 1 q gq u of t plus h minus 1 q y of t. So this is really h minus 1 q y of t minus gq of t, right? So we have seen that LQ, the filter, well, gives you an extra freedom, and in the frequency domain, well, I've said you can use it to orient the fit in certain frequency ranges, but you can also see it as, well, the removal of high frequency disturbances, of a slow drift and things like that. So the interpretation of the filter, right, is, if you have a filter over here, it's equivalent of working with UF, the filtered input, and YF, the filtered output. So in practice, if you want to do prediction error methods with a filter, what you'll first do is filter your input and your output. Okay, so if you look at that and you look at this expression over here, all right, and you inject it in here, well, the expression of the filtered residuals is like here. Here we have a minus 1 and a minus 1 over here, and so this is indeed LQ. But why do we write it like this? Well, you can see that really, if you do filtering of the residuals, okay, and you use this filter in the predictor error identification, well, you really are changing the model to what it was in your actual model structure to the model, the noise model that you have over here. Okay, so filtering the residuals or using this filter to filter the inputs and outputs is really changing the model structure. Well, this doesn't make too much sense in general, okay, if your noise model is flexible enough, but it can make sense if, for instance, your HQ is fixed, right? So if your HQ is fixed and you have, for instance, an output error model, then you know that HQ is equal to 1. Okay, so what you could do in this case is do output error identification, and then you work with a filter LQ, and this means that in reality you're working with a fixed noise model that will be 1 over LQ. But in general, when the noise model is general, in the sense that it's different from one, well, typically filtering is not used. So the standard choice for this positive function is the following one. So in practice, we'll minimize the sum of squares of the residuals. This is because we've seen in the course of linear algebra is that, well, very often for certain model structures such as ARX and finite impulse response models, this will lead to a least squares problem, and this is nice because, well, we have a neat way to compute the estimate and we do not run the risk of a local minimum. For other model structures, we'll have to use numerical optimization, but this is kind of a nice function to work with, so it's okay. The downside is that it is not very robust to outliers, and it's easy to explain. If you have an outlier, epsilon is large, but epsilon square will be even larger, so you'll focus on this outlier, which is not a good thing. So you could think of other functions such as L epsilon is absolute value of epsilon, but that is, well, not a very good function to work with when you do numerical optimization, and you would also lose this property over here. Just I want to mention that you can also work with time varying norms, in which you kind of forget exponentially, for instance, the old data, so that you forget them when they become less reliable. But these are all things here that are there for your information, as you can see. We have seen, when we have considered the one step ahead prediction of y, that you can write the predictor as follows. This is a nice little formula because the theta come in linearly, and the regressor, as you can see over here, is independent of theta. So if we write the criterion and the prediction error criterion, well, this is the one step ahead prediction, right? And you can see that this is really a least squares problem. So it's quite easy to write the theta that will minimize this function. Okay, so it looks like this. It looks a bit different to what we've seen before, but if you have had a course on linear algebra, and you have, well, you should be able to find this quite easily. So we are working with an ARX model, and we have just seen that you can write the one step ahead prediction in terms of the regressors and the parameter vector, and you're given a data set Zn, well, with n data, n input data and n output data. So the idea will be to say, well, we have to make sure that y hat, and the one step ahead prediction, is equal to y. You want to impose this, and you want to impose this for, well, the n data points. So what you can do is write this in matrix format. So this is y1, right, is equal to, and then we have to use this equation over here, and what we'll have over here is theta 1 up to theta d, right? This is theta over here, and of course d is equal in our case to na plus nb, right? And if we write the equation in times t is equal to 1, we end up with phi transpose 1. Okay, of course we can write this equation for time t is equal to 2, and we can keep on doing this up till yn over here, and we have then phi transpose n. This is a system of equations, right? There are n equations, and there are, well, d unknowns. So obviously there is no solution, okay, but there is a solution in the least squares sense. So we've seen this. We'll call this y, and we'll call this phi. We know that, we'll call it like this, it's phi transposed phi minus 1 phi transposed y. Okay, so we have seen that the expression in the previous slides was a bit different, but that shouldn't be a problem if you write this thing over here. So phi transpose phi, well, this is a, well, if you transpose this one, what you'll have is this one over here, phi 1 phi 2 up to phi n, and then you have to multiply by phi. So this one was phi transpose 1 phi transpose 2 up to phi transpose n. Okay, and then this matrix is organized in columns, this one in lines. Well, we have seen in the course of linear algebra that you can write this as the sum where t is equal to from 1 to n of phi t phi transpose t. You can do something similar for phi transpose y, and what you'll have is a sum ranging from 1 to n of phi transpose y of t. Okay, so what you can do, since they are going to cancel out anyway, so it's this one, and you have to, well, pre-multiply by the inverse of this one. You can put an 1 over n in the front over here. They will cancel out. So this is the estimate that we have obtained, so you can write it as Rn inverse f of n, where Rn and Fn are defined over here. So here you have to take an inverse. Of course, this matrix has to have an inverse, so you can check the rank of this matrix. If, well, this matrix is ill-conditioned, so that it is almost singular, well, you could have problems. But normally, if you have done your experiment design sufficiently well, in the sense that you have excited the system enough, and that you haven't chosen the number of parameters too high, this should not be a problem. So checking the rank of this matrix might be a test to see if you have not over parameterized your model structure. So this matrix over here is really constructed from covariance estimates, so cross correlations of y with past y's, with past u's, and so on. Well, let us have a look at that. What I've done over here is, well, really show the regressor in the case of the ARX model, right? So this is this matrix R of n. I'll simply write it as R, and then we have here what we had called F of n. So that this is a matrix, right? And this is a vector, right? So let us look at element R11 of this matrix over here. So this one is a column vector, this is here a row vector. So in this sum we have a sum of matrices. So what we have to do now is look at how the first element is constructed, and if you look at that, it's 1 over n, a sum where t ranges from 1 to n of yt minus 1 times itself, so squared. Okay, so this is, well, constructed, and it's an estimate of the variance. Okay, so this is an estimate of the variance of y. So R12 will be 1 over n, a sum of t is equal to 1 to n, and then we'll have yt minus 1, yt minus 2. So there we correlate a y with a previous y. So this will be an estimate of yt minus 1. Okay, and so on. So you can see that this matrix is contained of estimates of correlations of y's u with previous y's, previous u's, and so on. Here is a nice summary that you can use in the system identification laboratory, because you'll have probably to implement your own ARX function to identify an ARX model. And it's here that you can clearly see the link with the course of last year, linear algebra and applications. So remember that the one step ahead prediction can be constructed as follows. For the ARX model, it's nicely linear in the parameters, and the regressor is independent of the parameters, right? So we have seen that you can take this regressor, it's a row vector, so you can stack them, these rows, one above the other, and you end up with this matrix phi, right? And as you can see, phi will be n times d. D is equal to na plus nb. So when you're writing your own ARX function, check if you construct phi that it has the right dimensions. And y is constructed as follows. Okay, so it's a vector, a column vector, right, with n components. Well, using these equations you can write the following system of equations, and since, well, usually n will be much larger than d, there will be no solution in the classical sense, but there will be a solution in the least squares sense, as we've seen before. And as I've shown you, the least squares solution is this one. In practice, since you're going to implement this in a MATLAB, you should write this as follows. This is something that, of course, makes the link with the course of linear algebra. So I don't want to see this implemented, because this might lead to numerical problems. What is very important, and you'll see this when you implement your own ARX function, is that initialisation has to be taken into account. Let us have a look at this initialisation problem more closely. And what I've done here is rewritten all the information that you need. What you have over here is the one step ahead prediction. It's constructed from the theta. Well, they are constructed from A1 to ANA, B1 to BNB, and it's also constructed from the regressor vector. So keep this structure in your sight so that you see what is happening. And, well, the system of equations, okay, that you have to solve is the following one. Remember that n in this case will be much larger than D. Okay, so that you have really a least squares problem. So it's really a good idea to have a look at this matrix phi and, well, fit it in, at least in the beginning, so that you see that there is a kind of structure over here. So if you write the regressor at times t is equal to 1, you will see that you have minus y0, minus y1, minus 1, etc. Right? And then you write it in t is equal to 2, minus y1, minus y0, etc. t is equal to 3, minus y2, minus y1. So do you see this structure that is appearing over here? You have one column, and you can obtain the next column by shifting in this direction. So there is a kind of structure over here. So when you implement your ARX model, please check if you have this structure. If you do not have this structure, it doesn't make sense to go any further. Okay, so what is the problem of initialization? Well, this matrix here, phi, is constructed from, as you can see here, y0, y minus 1, but we have only access to y1 to yn. Okay, so when you construct this system of equations, there are elements that are unknown. So there are two options. First option, if you do not know it, you replace it by 0. But this will kind of influence your estimate, so this is not really a good idea. The best idea is just to write this and see, well, if I have here in my system of equation one equation when the data is not available, and this is clearly, for instance, the case for the first equation, well, you simply cross it out and you don't take it into account, right? And obviously I have to cross out the corresponding element in y. So this is something that you have to do in your ARX function. You have to keep on crossing out equations until you find an equation over here where all the information is available. So for instance, if NA is equal to 1, right? Well, then you see here that at some stage, and it will be, we'll still have to cross this equation out. But at this stage, well, we'll start with the u's. Okay, so you see that after two equations, and 2 here is a hint, it's after NA plus 1 equations, you have all the information for the y's that is available. Okay, but you can see over here that you also have u's available, so you also have to have a look at, well, is my information for the u's available? Okay, so really you have to cross out a number of equations, and this number of equations will be dependent on NA, NK, and NB. And so this is something that you will explore in the system identification lab. What is also nice is that, of course, we have here a data set Zn. What could be done also is, for instance, that you're given one data set with N1 data and a second data set with N2 data, and that you want to use both data sets to come up with an estimate of data. So this means that you would have this initialization problem for the first data set, and you would have it again for the second data set. But this is something that can be done, and maybe you will have to explore this also in the system identification laboratory. Well, we have seen that for model structures other than ARX, so for instance ARMAX, output error, and so on, the regressor is theta dependent, right? So the prediction is no longer nicely linear in theta because of this theta dependence of the regressor. So if you write the criterion for prediction error identification, you can see that you have a so-called non-linear least squares. Okay, you do not have this linear least squares problem that we had for the ARMAX model structure. So this means that we need to use numerical methods, and these have been covered in the course of optimization methods, right? So we have to use this general family of search routines that is, well, described by this equation over here. So the new estimate is constructed from the previous estimate by computing a search direction and taking a step alpha k in this search direction, and then you'll hopefully converge, but the problem is that you'll converge maybe to a local minimum. So what you can do is choose different initial values, and hopefully you'll select one for which if you run such a search routine you will end up in the global minimum. Well, we have seen last year in this course of optimization methods that if you have to minimize a function f of x with respect to x, well, one descent direction is minus the gradient of f of x with respect to x. Okay, and we had seen that here the speed of convergence, and I referred to the optimization cost, is really linear. Okay, so let us consider our nonlinear least squares criterion for identification, and I'll rewrite it as 1 over 2n sum t ranging from 1 to n, and we'll write it as yt minus y, the one step ahead prediction, and the whole thing squared, right? So this is here what is playing the role of f of x. Okay, so to obtain this descent direction we must compute this gradient of this function with respect to not x now, but with respect to theta. So you can see this as the gradient of this function Vn with respect to theta. This is just another notation. So if you take this gradient, well, what you have is you'll take the derivative, so you'll have 2 times 1 over 2n, so these one will cancel out, and then you'll have the sum t is equal to n. So this is really the gradient here of this Vn with respect to theta. So this is epsilon, right? Prediction error. So you have a square here, so derivative of epsilon squared 2 times epsilon, the 2 is there, so here we'll write epsilon and then we have to take the derivative of epsilon. So here we have this, so we have to take the derivative. This is constant, so to take the derivative it will give a 0 contribution, so it will be minus the derivatives of these quantities with respect to all the parameters. So I'll put the minus in front, right? And here we'll have, well, the derivative or the gradient of the one step ahead prediction with respect to theta, right? So here we've called this thing over here psi t theta, and so this is how we obtain this expression here. Okay, as I've said, psi t theta is the gradient of the one step ahead prediction with respect to theta. So this is really a d-dimensional vector. Okay, so this quantity over here is a vector. So this is the situation. We have a non-linear least squares criterion for identification. It's based on the prediction error, and we have computed the gradient of this cost function with respect to theta, right? And we have obtained this in the previous slide. Remember that we had this routine or this family of search routines, right? And if you take dk is equal to minus the gradient, right, what you obtain is a so-called gradient search. So here you have the summary. This is the update equation that you have to use for theta. Remember that the new theta is the previous one with a step in the search direction, and the search direction is minus the gradient, so you simply take this one with a plus sign. Okay, so this is really the search direction. Remember that psi t theta is really the gradient of the one step ahead prediction with respect to theta, and we'll see later on in the slides how you can compute this for a given model structure, and we'll consider the ARMAX model structure and the output error model structure. We have seen that, well, this gradient search is fairly inefficient, close to the minimum, and also that the speed of convergence is linear, right? So therefore we had considered in last year's optimization course an idea of using the Hessian. So the Hessian is the, well, really the second derivative, and to use that type of information, and this leads to Newton's method, and this method is quadratic as far as the speed of convergence is concerned, at least close to the local minimum. So the update equation is the same, right? And for Newton's method, alpha k, the step size, well, is generally chosen slightly less than 1. So close, equal, probably a little bit less than 1, right? And the search direction involves, of course, the gradient with a minus sign, and you kind of correct this by the inverse of the Hessian, right? And the Hessian is obtained from the gradient by taking a derivative. So the gradient is a vector, but the Hessian is really a matrix, and if theta contains, well, d parameters, this will be a matrix that is d by d. So what we do here is compute the exact Hessian, and for that we start, of course, from the gradient. The gradient is given over here. So it was minus 1 over n, a sum t is equal 1 to n of ct theta times epsilon t theta, right? So we have to take the derivative of this one with respect to theta, and you can see that there will be two terms, one that will involve the derivative of this one with respect to theta, and this is this one over here. Remember here that this is y minus the one step ahead prediction, right? So if you take the derivative here, there will be a minus sign, okay, so that will cancel out with this one. So this is explains why you have a plus sign over here, and then you have the derivative of this one, or the derivative of the one step ahead prediction with respect to theta. And so this one is over here, and the derivative, well, the minus sign disappears because of this one, and this really is again the derivative of the one step ahead prediction. If you take the derivative, well, again you'll have a psi, and you have to have a matrix over here. This is why you have psi times psi transpose. Okay, and the other term will involve, of course, the derivative of this one, right? So the a matrix here times epsilon, and here we'll keep the minus sign. So the expression of the exact Hessian is as follows, but in this second term here you can see that if you converge and epsilon becomes small, this second term has a contribution that becomes smaller and smaller. This is why often, because computing the exact Hessian is computationally expensive, we replace the Hessian by an approximation. Okay, and this approximation is simply taking the first term in the previous expression, and the advantage is also that by doing this approximation we obtain a matrix here that is really positive definite. This is something that we have seen last year in the course of linear algebra. So go and have a look if you have forgotten the concept of a positive definite matrix. This yields the Gauss-Newton descent method. The update equation is the same. Alpha k is chosen close or equal to 1. In general, we'll take it a little bit smaller than 1, and what we do here in this descent direction, we use this approximation. So it's minus the gradient, and you have this correction with the inverse of this approximation of the Hessian. And if you plug in right in here, and if you also take the expression of the gradient of the cost, which is this expression here, you obtain an expression of the Gauss-Newton descent direction, and this looks a lot like a formula that we've seen when we've computed, well, the least squares estimate in the case of an ARX system, right? This means that you can rewrite this using matrices. Okay, so dk, you can write it as follows. We'll have to use matrices. So this is this psi matrix, but it's a matrix, so I'll put a bar over here. Of course, this psi matrix, I will show it, is constructed from these psi that are over here, right? And then psi transposed, and then E, right? Well, psi, the matrix psi, is constructed from this psi over here. Remember that psi is the gradient of the one step ahead prediction y hat with respect to theta. So how we'll construct this psi is by taking the psi that are over here, evaluate them in 1. I won't write the dependence on theta to make it a little bit easier to write, right? Then the second row, and then up to psi n, right? And E here will simply be a vector containing epsilon 1 up to epsilon n, right? And if you look at this is correct, right? Because if we write, I'll write it up here, psi transpose psi, so this is then, well, here of course there is a transpose, because the gradient vector is a column vector, so you have to transpose. So if you transpose this matrix, we'll have C1, C2, up to Cn, right? This is this one over here times this matrix over here, C transpose 1, C transpose 2, up to C transpose n, right? And this you can write as a sum. T is equal to 1 to n, right, of C T C T transpose. Okay, so this expression is correct because you see it here that really the 1 over n, they cancel out. Okay, we like this expression here because it's organized in terms of matrices. So this is what we've written over here. So this is the C matrix in my previous explanation. The E matrix, we've seen that the descent direction, this is really Gauss-Newton, right? Gauss-Newton direction can be written like this. Of course, you know from last year's course of linear algebra that you won't write it like this, but that you will write it like this. So at iteration k, this is really what this is meaning. The Gauss-Newton direction is obtained by this equation. This matrix here is this one evaluated at theta is equal to theta k. Okay, and E here is the associated prediction error vector. Okay, so what we need now in order to construct this C matrix is to compute this gradient vectors for the relevant models, and what we'll do is consider ARMAX models and output error models. Okay, and as we have done for the computation of the estimate using least squares of the ARX model, you have to take initialization issues into account, but this is something that you'll do and that you'll try in the system identification laboratory. Well, we have seen how you can obtain the Gauss-Newton descent direction using this matrix R theta, which is an approximation of the Hessian, and this matrix is positive definite. You could still have problems in the sense that this matrix might become close to singularity. Okay, so if the matrix is singular, there is no inverse. Well, if it's close to singular, there is an inverse, but you'll have numerical problems. Okay, and this can happen if your model is over parameterized. In practice, this means that you have used too many parameters in your model structure, or that your data is not informative enough, and this would mean that you didn't do a good experiment design. So we have seen in the course of optimization methods that you can use regularization, and this is called the Levenberg Marquardt procedure. And what you do is replace this matrix by this expression over here, where this is the identity matrix and lambda is some positive scalar that you will choose small in general. If you plug this in, you obtain this new descent direction, and it's known as the Levenberg Marquardt method. If lambda is equal to 0, you have of course the Gauss-Newton direction. So in practice, how can you implement this in MATLAB? Well, you have to first construct this matrix R, right? And you will not do this with inverse of R times this matrix. You'll implement it as we've seen in the course of linear algebra and application using this backlash operation. in order not to have numerical problems. And in the background there is this elimination procedure that we've seen last year. So what we need now is to compute the psi theta, which is really the gradient of the one step ahead prediction with respect to theta. Why do we need this? Because when you're at iteration k and you want to obtain theta k plus 1, you need the descent direction, and this descent direction will depend on psi of t theta k evaluated at theta k. And given all this, you'll be able to compute the new estimate. So what we'll do is compute this gradient vector for output error models and also ARMAX models. So for output error models, the predictor is given as follows, where b q theta is b1 q minus nk up to b and b q minus nk minus nb plus 1, and here f is 1 plus f1 q minus 1 plus f and f q minus nf. So now we have to take the derivative, okay, and so we'll do first the derivative with respect to the b's and then to the f's, right? So if we take the derivative with respect to the b's, and I'll maybe do it with respect to b1, okay, well, you have 1 over f because it's not depending on the b's, right? And then you have to take the derivative of this one over here with respect to b1, and what you'll have is q minus nk u of t, right? This one is u of t minus nk. This is exactly what we've done, but we've done it for all k's at once. If you plug in k is equal to 1 over here, this will cancel out and you'll have u of t minus k as we have over here. So this is the expression when you take the partial derivatives with respect to the b's, and here is the expression when you do the partial derivative with respect to the f's, okay? Here they are at the denominator, so obviously you'll have minus 1 over f squared times b, and then you'll have to take the derivative with respect to the corresponding parameter, right? So this will lead to this expression over here, right? So you can see here, since b over f applied on u is the one step ahead prediction, that you can rewrite this as follows, right? So what you can do to obtain these gradients is take, in this case, the input and filter it by 1 over f. If you're at iteration k, you'll have to take the f theta k, right? And here, to obtain this gradient signal with respect to the f's, you'll have to construct first the one step ahead prediction evaluated at theta k, and then filter it by minus 1 over f at theta k. We have seen that the derivative of the predictor, the one step ahead predictor with respect to the b's, involves delayed versions of this signal over here, and we don't want to write this 1 over f all the time, so this signal we'll simply call it uf, u filtered by 1 over f. And the partial derivatives of the one step ahead prediction with respect to the f's involves filtered versions of the one step ahead prediction. and it's again this 1 over f. Don't forget that there is a minus sign over here, and this signal, we'll call it yf hat. It's the one step ahead prediction filtered by minus 1 over f. And you can now construct the gradient vector at time t as follows. So this is really, and because the order of the parameters is of course important, so it's b1 up to bnb, and then f1 up to fnf. So you can see here that this one is the partial derivative of the predictor with respect to b1, and so on. We will now compute the gradients, but for ARMAX models, remember that the one step ahead prediction is hq theta minus 1 gq theta u of t plus 1 minus hq theta minus 1 acting on y of t. Gq theta is b over a, h is c over a, so this is the one step ahead prediction that you obtained. We had also seen that the prediction error is hq theta minus 1 y of t minus gq theta u of t, and if you again plug in everything that is needed, right, you obtain this expression over here. So well, you can now use both expressions to obtain expressions for the gradient. So if you take this expression over here and you take the derivative with respect to the a's, well, this one is not going to give a contribution, this one is not going to give a contribution. We'll keep the minus 1 over c, and then we'll have to take derivative of this polynomial acting on t, and so this will give delayed versions of y, and it will all depend on which a that you take to see how much delay there is. For the derivative with respect to b, you have something similar. This term will not give a contribution, we'll have 1 over c and then delayed versions of the input. When you take the derivative with respect to the c's, you'll have again this minus 1 over c squared, okay, appearing. You've got it here and you've got it over here. We have already a minus sign here, so this explains the plus. In this case here you keep the b, and here you'll keep the a, b, a, and in this case we'll work with delayed versions of the inputs, and here delayed versions of the output. But using this expression over here, you can simplify this, and this is really 1 over c acting on delayed versions of the residuals. Okay, so you can kind of see here that there is all the time 1 over c acting on something. For the derivative with respect to the a's, it's the delayed outputs. For the b's, it's delayed input, and for the c's, it's the delayed residuals. Okay, notice here that the regressor vector phi is constructed from the minus y's, the u's, and the residuals. So here there is a link between the regression vector, this one, sorry, phi, and the gradient vector, and this relation is this 1 over c. So we can now obtain the gradient vector ct theta. Remember that the order of the variables in the vector theta is as follows: a1 up to a and a, b1 up to b and c, and c1, no, it's b of course here, c1 up to c and c, right? So this explains that over here you have really the partial derivative of the one step ahead prediction with respect to a1, right? So the last one over here will be with respect to a and a, and this one here is the partial derivative of the one step ahead prediction with respect to B1, and here you'll have the partial derivative of the one step ahead predictor with respect to C1. We have seen that these expressions over here, and over here involve delayed versions of these signals over here. This is what we've seen by computing the partial derivatives. So in order not to write this 1 over C all the time, okay, we define this signal YF, UF and epsilon F. Well, here pay attention, the minus 1 over C is taken into account. This is why you have a positive sign over here, right? So this is how you can construct the gradient vector for ARMAX models. So what you see here is a kind of pseudocode or algorithm that will help you to implement, for instance, an output error function. Okay, you will have something very similar for the case of the ARMAX model. So the first thing that you will do is identify an ARX model, and this is just to have a good initial estimate. Remember that this is a numerical method that we are implementing, so depending on the initial conditions you might end up in a minimum, local minimum or not. Okay, so it's very important to start from a good initial condition. So the idea is to use the ARX model that you have identified as a starting point. So what do I mean by construct theta 0? Well, if you identify an ARX model, the order of the parameters is, well, first the A's and then the B's, but for an output error model it's the B's and the F's. Okay, so the A's of the ARX model will become the F's of the output error model. So there is some kind of reordering to do here. Once you have theta 0, what you can do is compute the filters or the polynomials over here, B and F, well, initialized in this version theta 0 of the parameter vector. And then really this is going to, we are going to start the iteration, and so we are going to repeat what is in here, and of course you need a stopping criterion. It could be very easy, just the number of iterations. I'm going to do 10 iterations, or it could be a number of iterations and then looking at the prediction error, or it could be looking at the variation of the prediction error, and so on, right? So here you need a stopping criterion that will kind of make you leave this loop over here, right? So based on your current estimate of theta, if it's the first time you enter this loop, it will be theta 0. Otherwise, it will be the one that you've computed here at the end. What you need to do is construct these signals, okay, these filtered versions of the input and these filtered versions of the predicted output. Okay, so I refer to the slides on the formulas that are behind this. Once you have those signals, you have to construct this matrix Psi over here, right? And to construct this vector E over here. Okay, this one is composed of the residuals, the n residuals, and this one is constructed from, well, the gradient vector that you have to transpose and evaluate at 1, 2, up to n over here, right? So once you have this, well, you have everything that you need to construct the descent direction, right? And here I've written this in MATLAB notations. Once you have the descent direction, you can do the update of theta with alpha k, a value that is close to 1 but probably a little bit less than 1. And when you have your new parameter theta k plus 1, you can construct your new polynomial b, you know, new polynomial f, and return over here, right? So what could be added over here is this regularization, okay? There is this matrix R that could be ill-conditioned, so have a look at the notes. And of course here you'll have to think about initialization, because in here there might be signals over here that, well, are not available, right? So you'll probably have to skip a few rows over here and over here. So you'll have the opportunity to test all this in the system identification lab, either on an output error model structure or an ARMAX model structure, or maybe even another model structure that is a bit more complicated.